You know, if you follow the world of tech, you hear it constantly. Artificial General Intelligence, AGI, is right around the corner. It's this story of inevitable world shattering breakthroughs. But what if that entire idea is built on a huge misunderstanding? Today, we're going to dig into a really powerful counterargument that's grounded not in philosophy, but in the hard, cold laws of physics. And yeah, this feeling, this quote, it just perfectly captures the dominant story, doesn't it? Especially in places like the Bay Area, it's become a bit of an echo chamber. The same ideas about just scaling everything up to get to superintelligence just get repeated and amplified, and they often go unchallenged. It's a really exciting story for sure, but is it a realistic one? That's the big question we're really exploring today. We're going to try and step outside of that echo chamber and look at this whole problem from a completely different angle, one that starts with the physical reality of how our computers actually physically work. So how are we going to cut through all that noise? Well, we're not just going to list a bunch of different opinions. We're actually going to build a case from the ground up. We'll start with a simple, undeniable truth, and then just follow the logic, step by step, all the way to its conclusion. This is what you call an argument from first principles. All right, so here's our roadmap. We'll kick things off with what we're calling computation's physical leash. Then we'll see how we're hitting a physical wall. From there, we'll dive into the fallacy of just scaling everything up, compare how different global players are approaching this, and then finally, we'll deconstruct the whole fantasy of superintelligence itself. So let's jump right in. Okay, so this entire argument really hinges on one foundational idea. It's something that gets overlooked so often in all the abstract, philosophical chats about AI. And it's the super simple idea that computation, well, it isn't magic. And this, right here, is the crucial point. Every single thing that happens inside an AI model, every single calculation, is a physical process. It burns energy. Information has to literally physically move from one point to another. This is not a thought experiment. It's engineering, and it has real-world physical constraints. So let's really compare these two ways of thinking. In the abstract, you might think, oh, intelligence is just software. You can scale it forever. But in physical reality, that software needs hardware, and moving information across that hardware has a very real cost in both time and energy. You see, progress just isn't inevitable when it smacks up against the hard limits of physics. And hey, we have a perfect, concrete example of this principle in action, right inside your computer's processor. The memory cache. L1, L2, and L3 cache, they're all made of the same stuff. But L1 is the fastest simply because it's physically the closest to the core. Distance matters, period. As you scale things up, they get slower because information has to travel farther. And you know what? This isn't just true for silicon. It's true for us, too. Nature already figured all this out. You can predict a primate's brain size with almost 99% accuracy just by knowing how many calories it eats. And we humans? We are right at a physical boundary. Our brains are so incredibly energy hungry that a pregnant mother can barely provide enough energy for her own brain and a developing one. So you see, even natural intelligence is on a very tight physical leash. Okay, so if computation is physical and it has real limits, what are the consequences for all the crazy progress we've been seeing in AI? Well, as we're about to see in this next section, it means we're about to hit some pretty serious breaks. This is a fundamental law of diminishing returns, and it applies to literally everything, from particle physics to AI development. To get that next 10% improvement, you don't just need 10% more resources. Nope, you need exponentially more. All the easy gains are found first. After that, progress gets unbelievably expensive. This timeline just illustrates the point perfectly. The whole AI boom we've experienced was powered by these massive generational leaps in GPU efficiency. But the reality is, we hit peak performance per dollar way back in 2018. The improvements we've seen since then have come from some clever, one-time tricks, but that well is now running dry. The era of exponential hardware gains is over. So these were those one-off features that gave us those huge performance boosts. We figured out how to use lower precision numbers. We added specialized hardware like tensor cores. We improved memory. But the thing is, these are not tricks you can repeat over and over. We've basically picked all the low-hanging fruit, and there isn't another true of easy innovations just waiting for us. Now, I know what you might be thinking. The most common response to all of this is, okay, so what? We'll just build bigger data centers and scale it up. Well, this section is going to tackle that exact argument and explain why just adding more isn't the magic answer it used to be. This slide shows the whole story. In the past, we were on a rocket ship. A little bit of money bought us huge performance gains. Now, it's like we're on the hamster wheel. We have to pour in exponentially more money and resources just to get the same linear progress. The economics have completely, totally flipped. So how much time is left on this path? According to the source for this explainer, Tim Dettmers, this is how long we have. About 1 to 2 years left of making meaningful progress just by scaling things up. After that, it becomes so physically and economically expensive that it's just not going to be feasible to keep going like this. That wall is coming, and it's coming fast. And this creates these massive risks for any company that's betting their entire future on building bigger and bigger infrastructure. I mean, what happens if some clever, smarter software innovation comes along that completely outpaces brute force scale? Or when efficient open source models get so good that anyone can deploy them? That multi-billion-dollar hardware advantage could just vanish almost overnight. So you see, these physical limits aren't just an engineering problem. They are actively shaping global AI strategy. When you zoom out, you can actually see two very, very different bets being placed on the future of AI. In the US, the dominant philosophy really is winner take all. The goal is to build the one single best model, the AGI, with the belief that everyone will just end up using it. So success is measured by raw capability. China's approach, on the other hand, is fundamentally different. It's all about what they call economic diffusion, integrating good enough AI into every single corner of the economy. For them, success isn't about having the one best model, it's about achieving widespread productivity gains across the board. And this brings us to the final part of the whole argument. We're going to take all of these physical principles that we've laid out and apply them directly to the ultimate goal of that winner-take-all strategy, the creation of a super intelligence. This is the idea that has just captivated so many people. The theory is that once an AI becomes as smart as a human, it can start improving itself, creating this wild feedback loop that leads to a runaway explosion of intelligence. It's a really powerful story, but it treats intelligence like it's some abstract concept, completely disconnected from physical reality. And this is the grounding question. This is the one that pivots the entire conversation from the philosophical world to the practical one. Forget about what a superintelligence could think. What could it actually physically do in a world that is governed by the laws of physics? And the answer is it would face the exact same physical walls that we do. It can't magically invent better GPUs out of thin air. It can't just wish away the law of diminishing returns. It can't make an architecture like the Transformer dramatically better because its design is already incredibly efficient at moving information. It's already bumping up against the physical limits we've been talking about this whole time. A superintelligence does not get to cheat physics. Any improvements it could make would be incremental, not explosive. So we're left with this final thought. Perhaps this whole race for some mythical, godlike AGI is a distraction. If the path to ever greater intelligence is blocked by these immense physical and economic walls, maybe the true valuable future of AI lies in the much more practical, and maybe much more difficult, challenge of just weaving what we already have into the fabric of our economy and our society.